Okay, so let's talk now about reductions. So, a reduction for between a language, LX to LY, is simply an algorithm such that you, if W is in LX, then W prime is LY, i.e. it's an algorithm that changes uh, an instance of problem X into a instance of problem Y, okay, through some means, okay? It's just an algorithm that encodes W into W prime, okay, so that if W is in LX, then W prime will be in LY. And if W is not in LX, then W prime would not be in LY. Okay, so that's what a reduction is with languages. With decision problems, a reduction works such that if IX is a yes instance of problem X, remember we're talking about decision problems, so that the output of decision problems could only be yes or no. So if the instance of X is a yes instance of X, then the instance of Y is also a yes instance of Y. Okay? So so we need an algorithm that transforms yes instances of X into yes instances of Y. Okay? And even though we're writing this reduction, even though this is a double arrow here, reductions aren't always two ways. It's very possible that you could only do a reduction one way, i.e. you could reduce a easy problem into a hard problem. For instance, any problem that we talked about in the second part of the course, any of the algorithms problem, the recursion problems and stuff, we could turn any of those problems into 3-sat. Okay? But we can't turn a hard problem into an easier problem. Okay? So another way to look at that is addition is an easy problem. And we could turn addition into a graphing problem and into a pathfinding graph problem. But we can't turn a pathfinding graph problem into simple addition. We need more than that. So we use the reductions to solve the problem, i.e. if we have an algorithm for Y, then all we need to do, the reduction itself, is simply a function that turns the yes instance of X into the yes instance of problem Y. And similarly, if Ix is a no instance of X, then Iy has to be a no instance of Y. Okay, so it has to work, it has to be true for both yes and no instances. But the reduction here is just a function. Okay, it is just a encoding function to encode the input of X into something that Y will take in. Okay, so if X is a graphing problem and Y is some number set problem, then you got to figure out how to turn a graph into a number set. Okay, so another way to show this reduction is through a diagram. Okay, this is my preferred way. Simply put, this diagram shows the exact same thing as this code here. You have a algorithm for Y, and all you're doing is taking an instance for X, you're putting it through a reduction so that it turns into an instance for Y, and then once Y outputs yes or no, then that will become the X output. Okay. So let's say the running time, Rn, is the running time of the reduction, and Qn is the running time of the algorithm that solves Y. Then what is the running time of Ax? Now remember this function here. Okay? Remember this function here, namely that we want to return, this algorithm returns ax of iy, which is simply equal to ay of r times ix. So what would the running time of the algorithm for x be? It would just be nested function. Here. Oh, sorry. The nested functions. Q of Rn. So, another way to look at that is if Ix has size n, then R creates an instance of Iy of size at most Rn. That's the maximum that it could create, that size of Iy it creates. And Ay's time on Iy is by definition at most Q of Iy, which is simply equal to Q of R of n. So, in more concrete terms, if the reduction takes n squared time and the algorithm for y takes n to the 1.5 time, then the algorithm for x is simply the time of the reduction or the time of q times over the time for the reduction, q rn. Okay, so the reason we separated this out is that there could be instances where the reduction takes more time. For instance, the reduction takes, I don't know, n to the 4th time, but the output Iy is of size n still. In those cases, it might be fruitful to simply write n to the 4th times q plus n to the 1.5. You don't necessarily have to add them together, but that's a less common case. Usually, it's just this term. Okay, so reductions allow us to formalize the notion of problem x is no harder to solve than problem y. So remember the reduction direction. Okay, I keep saying this. If problem x reduces to problem y, then x cannot be harder to solve than y. Okay, and why is that? Look at this diagram. Okay, look at this diagram. If y is polynomial time and the reduction is polynomial time, then by definition, x has to be polynomial time. If, on the other hand, y is super hard, we know there's no efficient algorithm that, if on the other hand, if y is super hard, and we know there's no efficient algorithm that solves y, that doesn't really necessarily make x super hard either. We might just be choosing a hard y, right? We don't have to choose y. We don't have to choose this particular problem to solve x, right? We're trying to get a tight bound for the hardness of x. Okay, so we could show if y is easy, then x would also be easy. We could choose another problem where y is hard that still makes this reduction work. That doesn't mean x is hard. If, on the other hand, x we know is hard, if we know this algorithm is hard, then whatever this reduction here, ay has to be hard also. If ay is not hard, if it's easy, then this whole thing breaks apart. X has to be easy. That's a whole contradiction, okay? So remember, reduction in direction. If problem x reduces to problem y, then x cannot be harder to solve than y. So if x reduces to y, we could say that x is no harder than y, or that y is at least as hard as x. And yeah. Okay. So we're going to be talking more about that throughout the lecture in the next couple lectures. I know it's going to get tiring, but it's really going to, I hope after the 5th time I say it, it'll really get cemented in your mind, because it's one of those fundamental things that you have to think of first. All right, let's go on.